By Professor Jeremy Baumberg from the University of Cambridge, United Kingdom. He is a leading innovator in nanoscale optical materials. He is the fellow of the Royal Society Optica and Institute of Physics. Today, we will talk about Prince's Nanogap Metamaterial for checking higher analysis using the SERS and for the follow sensing. Let's warmly welcome.
Thank you. It's really great to be back in this conference. So I'd like to thank the organizers for giving me the opportunity to talk to you. And then I thought also what I'd do is I'd talk about a bit of a different topic than I normally talk about at this conference. So I'm going to really talk about sensing and how you can use metamaterials in sensing. And sort of the background to this, the motivation is that there's a huge demand for biosensors that look at small molecules. Because essentially the only way that you can really detect small molecules that are essentially the molecules that control all the feedback loops in our body is by mass spectroscopy. So it's essentially expensive. You send your sample off to a clinic. And there's a huge demand for sensors that are much lower cost than that. And that can work essentially all the time. So that's really where I'm going to go in this talk. And what I'm going to try and show you is that metamaterials have a really interesting place to play. So I'm going to go around a number of different areas that hopefully you'll see how it all comes together. So you've heard a lot about metamaterials already in the talk, in the conference. There's going to be a lot more. So I'm going to contrast the sort of metamaterials that are precision, designed, fabricated on very small scales for the optical domain, which are great, lots of really interesting properties, but very difficult for use for sensing because they rapidly foul and you're just going to have to throw them away all the time, and they're too expensive for that. So there's another sort of metamaterials where people are trying to use colloidal approaches to assemble intricate materials with properties that are neither those of the materials you're putting together. And the problem with all of these is that you have a large amount of disorder. It's very hard to construct the material that you really want. So this is the challenge. How do we do better than that? And then a number of years ago, we started to actually look at this area where we started to make photonic crystals on the kilometer scale using roll-to-roll assembly and shear assembly. But those are incredibly boring materials. Essentially, they're dielectric spheres just on a hexagonal lattice. So this is where we're going to go in a different direction. So I'm going to first start with this sort of so toy model, interesting problem. If I start with a chunk of metal, this is a chunk of gold, we'll all agree that in the optical domain, this has the real part of permittivity is negative. So then the question is, what happens if I cut a whole load of very, very small holes in that gold? So it's not completely obvious. And particularly if I make my slots here on the scale of a few atoms. So 99% of the material is still gold. So what is the effective properties here? And I'm going to look at wavelengths which are much bigger than all the dimensions of the slots and the difference between the slots. So this is a really good metamaterial. But what sort of metamaterial is it? Is it metallic or dielectric? And what I'll show you is that this system is in fact a very high index dielectric, very broad band. So as soon as I cut my slots, it looks like a glass diamond. So the question is then, what's the maximum refractive index that I can get? And we're going to get to this. So what we're going to really have to do is to cut really, really thin slots. And doing this in any sort of top-down approach is doomed to failure, I would say. We can argue about it. So I'm going to pick up on work that we've done over the last 15 years or so, where we've been looking at these very small gaps on the nanometer and sub-nanometer scale between, say, a nanoparticle and a gold mirror, and you put a very thin spacer, and you get incredibly high optical fields there. So that's what we really want to use here. So what we've now moved to is a system where we make sheets or chains, but really sheets of these nanoparticles with the same very, very small gaps. So I'll show you that we're able to do that. We call this a monolayer aggregate, and it's a very, very nice metamaterial is what I hope to show you. So the way that we do that is it's a really interesting process. It actually depends on liquid-liquid interface nanoassembly, which has been tried before in a number of ways, but the way that we do it turns out to give you these incredibly precise gaps on sheets that are really large scale. So essentially what you do is you take your gold nanoparticles in an aqueous solution, you float them on top of chloroform or another chlorine-containing solvent, and you add a connecting molecule. The molecule that we've used is called a cucubitrol, which we've used for a number of years. And what it does is it binds the gold nanoparticles together with a gap which is almost exactly 0.9 nanometers. So what happens is this, you actually take this, you shake it, and it reassembles into that structure, and what you get is a sheet of gold nanoparticles around the side. And those nanoparticles are so close together that the van der Waals interactions are hundreds of atmospheres, but the chemistry is really interesting in that it allows these gold nanoparticles to move around each other. So that's the droplet. So that droplet looks like it's gold, but that surface can still move around. So we can still get the gold nanoparticles to move around. In fact, then you can just pipette it up, you can drop it anywhere, you can do a lot with it, but it depends on this chloroform-water interface. So what we tend to do is we drop that on a particular substrate, and now we have a sheet, sometimes 1 monolayer, sometimes 2 monolayers thick. And although the structures aren't exactly uniform, so there's disorder in the system, all the gaps where the nanoparticles are touching all are 0.9 nanometers, so they all have the same gap plasmon frequency, which means that they can all couple together. So the secret of this system is that all of these gaps are coupled together, so it's something like a tight binding type of model. And we have these molecules in the gap, CBs, but they're maybe 10, 20% of the volume, so you can get many, many other things into the gap. So let's just think about what the perfect structure would do. So if these are some very nice calculations by Zongtan and Angela in Birmingham. So what we've been doing is looking at the periodic, say, hexagonal, triangular lattice here, where we have these gaps of 0.9 nanometers, and they have a particularly gap refractive index. So if you calculate if you do the full COMSOL simulations, and then you extract out what are the effective dielectric constants, what you find is in the mid-infrared, the refractive index is almost completely flat, and already in these systems it's something above 4, while at the same time, if you look at the loss in these systems, it's less than 0.5. So it's a broadband dielectric with a very high dielectric constant, and essentially what happens is the mid-infrared light travels through the material through all the gaps. It doesn't actually care about most of the gold that's there. It just threads its way through all the gaps there, and of course the gaps then generate a very large polarizability, and that polarizability is what's giving you this large refractive index. So if you look at that, then the key thing here is the gap size. As the gap size gets very small, this refractive index gets larger and larger. So this is the domain that we try and work in right over here. And then also, the way to think about this as well is if you think about these as capacitors, which are working on optical frequencies, then clearly the area of the capacitor will increase the coupling, so the area of this contact is also important. So as I increase the facet diameter here, so these are the facets, then the refractive index can easily go above 10. And I'll try and show you how we're going towards that. There's also as I said, you can actually think about this just using circuit models. It works really well because the gaps are so small that essentially you can think about the plasmon here as just an inductor and capacitor giving you an optical frequency resonance, and then you just have gap capacitances to everything else. And if you solve that, you actually find that you can get a very good fit to all this data completely analytically. So it just depends on the gap size. So that's going to let us do quite a lot of things. I won't talk about this work today where we're actually looking at how you can use these to upconvert CW light with CW visible light. So mid-infrared plus visible giving high-frequency visible. So you start to be able to make mid-infrared detectors. And if you want to see Caleb's poster later in the day, then you can talk about that some more. What I'm going to also now show you is that this really is a metamaterial. So what we can do is, when we've made each of these layers, we can just stack them on top of each other. So what you can see here is that that's one monolayer, then I have a resonance here, and as I stack the different layers, I see this resonance go across all of the mid-infrared spectrum. And you can see that when I actually cross all of the absorption lines of different molecules in the gap, I get very strong enhancement of those absorption lines, and this is what we call SEIRA, surface-enhanced infrared absorption. But what's really going on here? Well, in fact, this is the simplest manifestation of a slab of metamaterial. My metamaterial of all these nanoparticles with the very thin gaps can be thought as an effective slab of material. And I just get Fabry-Pérot resonances because it's high refractive index, so I get a reflection from the top and the bottom surface, they interfere, and I just get very standard Fabry-Pérot resonances. But the nice thing is, since I know the thickness of the system, I can easily now extract out what the effective refractive index, and indeed, in this case, it's over 4. So the nice thing then is we have very strong fields inside those gaps. That's where the mid-infrared field is. So anything that we put inside those gaps, we see very strong absorption for. And you can see that here, as these are, in fact, the lines from this CB molecule that are in the gap. So I can see them very strongly. But what I can start to do is I can start to look at, say, antibodies binding into the structure. So I can look at some of the amide bands over time. Or what I can also do, because I can actually bring my light in from underneath the structure, I can make a transparent substrate here, bring the light in from this side, I can start to do surface-enhanced infrared absorption in a flow system, which is normally very difficult because all of the water absorbs all the mid-infrared light. In this case, the light is just in the gaps, just in the region that I'm probing, and my liquid can go sort of in and out of those gaps. So for instance, now I can actually look at electrochemistry in real time. This is a very standard redox couple here. And I can see lots of different bands. These are different vibrations in the mid-infrared, which are changing as I'm doing redox on the molecules. And in fact, these are slightly strange already. Although this is a very well-known redox reaction, already there's some strange things going on about how the redox happens, how it breaks the symmetry of the molecule, which shows up in some of these bands here. So I said that one of the things that you want to do with this metamaterial is to increase the facet sizes. So you might have thought, oh, it's great, we can just assemble cubes, but cubes do not want to assemble in this way, facet to facet. It's very difficult to do that with such thin gaps. So there's another way to do that, and we'll go a bit further on this later, and what that's to do is to actually just use electrochemistry to deposit gold in the vicinity of the gaps, but do it in such a way as that the gaps don't close. And this is the difficult thing to do, because if you do electrochemistry on a gap that's 0.9 nanometers, most of the time you sinter it. But there's a trick that we managed to avoid that here, and we just cycle backwards and forwards, and what we can do is we can essentially grow gold. We start out with something like this, and you can see there's some sort of extra lumps on here, but really the facets are increasing. If I look at the Fabry-Pérot resonances, you can very clearly see that I haven't increased the size of the thickness of the structure, but my Fabry-Pérot resonances have gone to lower energy, so I immediately see the refractive index has almost doubled in this system. So I can start to tune the refractive index backwards and forwards just by controlling this facet size. The reason that we want to do this is because we want to bring the resonance to the same place as those molecules without having to make so many layers. So this is actually now, I think it's just 2 monolayers of the monolayer aggregate, and then we already reach this domain where the Fabry-Pérot resonance is on top of the molecular absorptions, which enhances our contrast. So this brings me on to this whole idea of, well, how can you really make impact in low-cost sensing? And I always use the example of a Fitbit, or the equivalent, which I don't know if people were wearing. Essentially, the only use for that is it tells you if you're alive or dead. Because what we really need for looking at human health is biochemical information, and it's very difficult to find a low-cost way to make a wearable that gets biochemical information. And in fact, most of the hormones and neurotransmitters are very small molecules, so you can't use all the antibody type of binding. So what you really like to track those is in time, every day, every week, every year, just to see how those cycles change, and we do not have a technology capable of doing that yet. So that's what this UK big program is based on, is can we develop a new low-cost sensing? So if we're trying to detect sort of molecules, there are various different strategies. One of them is you make a system which has a very sharp, it's a dielectric system, saying it has a very sharp optical resonance, which is then sensitive to anything binding, changing the refractive index. So for instance, these sort of photonic crystal slabs or whispering gallery modes. And the problem about this is you don't know what molecule attached. Something just changed. anything can change it, fouling, temperature. So you need some sort of control channel. You need some sort of selective binders to only bind particular molecules. So this is actually very challenging. One way we know very well from sequencing is using fluorophore molecules, which you can see, just a few molecules, but basically most of the biological molecules we're interested in do not emit light. So then you need tagging, and then essentially it becomes like lateral flow, and again it becomes an expensive technology. And then there are technologies like this infrared absorption I showed you, or Raman scattering, which are conventionally expensive, difficult, slow, not sensitive enough. So some techniques are looking things like lateral flow and trying to amplify them. But I'm going to show you this different domain here, which is surface-enhanced Raman scattering, which has already come up many times in the conference and, of course, is well known. So what we're doing here is that we are taking a system and then we're shining non-resonant light on it, and then there's some weak probability that will actually scatter down to the first vibrational state, and this photon is redshifted. So you shine in light, you ignore all the scattered photons. Most million photons come out exactly the same color, but a few come out different colors, and each one tells you what the vibrational bond is. So this is very nice. It's a tagless fingerprint of each particular molecule, but it's very, very weak. And that's where the photonic structures come in, because it scales as the field, the optical field in the material, to the power 4. And what I'll show you is that we can get field enhancement of 1,000 or so we get these very, very large enhancements in the total signal. So for a long time, we played with structures which I would call three-dimensional aggregates. So these are gold nanoparticles with these very small gaps, and they're three-dimensional. They float around in the solution, so they encounter the molecules we're trying to detect very easily. But the problem is, whenever you make a colloidal assembly, the nanoparticles that you use, they always have some organics around them. There's always some ligands to stop them coming together. By the way, the same thing is true if you use lithographic fabrication. There's always some oil from the system, organics in there. So one of the things that we learn when you're making sensors is that you actually have to make them clean to start with and then keep them clean. And I'll show you a little bit more of those issues. But when you do this, for instance, we're using the CB molecule, which looks like a bit of a barrel. It's that molecule there. We use that to space the gaps. We see these Raman signals, which are the molecules, and then we actually look at other molecules, and you can see them appear in this spectrum here, where they've lost different amounts of energy. So this is the strength of the vibrational bond. So now what we're going to do is, instead of using these three-dimensional aggregates, we're going to use these two-dimensional aggregates which are fastened down to a substrate. And the reason that's going to be important is now I can do something with them. I can remove all the organics from the system. I can start to flow things through them, and you'll see that actually makes a profound change in what we can do. So as I said, the best way to think about this is if each gap is the same size. So this talk really is about how you need to have precision on the nanometer and sub-nanometer scale. If you do that, all of these are the same color, and then those plasmons can jump from gap to gap. There's a hopping probability there. So it's just tight binding that we all know and love if you think about nearest neighbors. So you get some band, and the lowest energy mode there is the one that's delocalized over the whole structure. It's delocalized on the scale of the optical wavelength, which means that external light couples into that mode very efficiently. So this is a very efficient way of getting light in and out of the structure. So I'm just going to show you one. This is actually going back to looking at a single gap. This is the capability of the technique. So even now we have these nanocavities here. Actually, even a single gold add atom looks to concentrate the field even smaller, which is why it's called a picocavity. If I have a carboxylate molecule in that gap, and I look at the Raman signature as a function of time, so these are the lines I was showing you before, I start to see things like this. I'm here looking at this particular molecule here. It's protonating and deprotonating. In fact, we can analyze that data, and we can extract the typical, this is the data of these different modes that you're seeing in the experiment. You can match it to DFT, and what it shows you is you're watching the flip of a single proton protonating and deprotonating from one molecule. So that's how good Raman scattering can get when you do this. And in fact, then you can define pH even of a single molecule, because you look over time and you see, how often does it stay protonated and deprotonated, and there's lots of interesting things that you can do with this. But now we'll come back to what we can do with sensing. And then this is the challenge between going from something where we know the photonics, we understand the photonics quite well, to making realistic sensors where we have to think about everything on the nanoscale. So many years ago, I commercialized this substrate here, patented it and developed it with Renishaw, which was called Clarite. And so it was, again, a Raman sensor, but now microfabricated. And you always had people complaining that when they got their Clarite, that it was contaminated. And we would ask them, well, where did you open it? And they would say, well, in the lab. And then, what's been in the lab? Because anything in the air will go down onto that sensor. That's the challenge of a very sensitive sensor, is that you have to present the molecules to it. And then we could also tell if our technician had been smoking cannabis over the weekend, because it would turn up on the sensors. So a lot of what I learned from this project was about packaging. How do you keep molecules from getting to your sensor? It's extremely tough. I no longer think that's a viable technique. And then the other thing to think about is, when we make these biosensors, we can't just make them unsustainably. I mean, the amount of plastic that came from COVID was absolutely enormous. So how do we go beyond this sort of problem? So we take these monolayer aggregates, and what we found is something quite magical, which is that we can clean them of all organics on the system and reuse them. And until this point, this has been extremely difficult to do for all SERS substrates. And the reason is because, as I was showing you, the morphology of the gold nanostructures is absolutely crucial, and you have to make a quantitative sensor that's the same all the time. So this is, again, showing you, this is the Raman scattering again. This is the CB molecule in the gap, which has this particular shape here. Now we're going to look at a small concentration of adenine. This is actually clinical concentrations here. So this is just a typical small molecule you want to detect. You see a line there. You see some other lines here. What we do is we oxidize the gold. So we normally think of gold not being able to be oxidized. But it turns out the top 3 atomic monolayers of gold will oxidize. And what you do is you then see everything else organic has gone from the system. You see there's a characteristic 3 lines there which tell us what sort of gold oxide it is. It plugs the gap completely, gets rid of everything else. We flow everything else away. That's a bit known, but actually the problem here is to regenerate that gap. So you reduce the gold oxide back to gold, but you have to do it without the gap sintering, which is what normally happens. And we do that. I'll show you a little bit more about how that works. But it does work fantastically. We come back to the same gap, and then we can just start again. And we can just go around this loop endlessly, hundreds, thousands of times. So we measure something, we clean all the organics out of the way, we bring our scaffolding molecule back in, and off we go. So this is really useful. What I'd say is that the ability to pre-clean the substrate when you want to use it is absolutely crucial. Re-clean it, and then also I'll show you that you can multiplex this incredibly well. So then there's a project we have at the moment, one of the many, which is called the intelligent toilet. What we're trying to do is pull neurotransmitters and hormones out of urine at clinical levels, and then these are this is dopamine and epinephrine and serotonin. You're just trying to pull it out, and you can distinguish them. So that's where we're trying to go to, but we have to make this a low-cost device. So just to show you the sort of things that we can do, so this is what I showed you to start with. This is the pre-cleaned system. This is just because we're going now through FTO. We've got a small package system so that we can actually do this easily in a flow geometry. So first we look at adenine, which I just showed you, then we clean it off. Then we look at cytosine, different spectrum, then we clean it off. Hypoxyxanthine, creatinine, and so on. And at the end here, we go back to adenine, and it's exactly the same spectrum as this. So just to show you, you can put molecules down, you can take them away. So this allows you this possibility of deep multiplexing. Now, I came from a background of, physics technology, but now I'm actually doing a lot of chemistry, which is great, I'd say. Really interesting, but it's surprising how little is understood about the molecule-metal interface, which is crucial for so many things, not just sensing, but electrochemistry, photocatalysis, a vast range of technologies. So here what we're doing is we're watching that oxidation process in real time. So these are the Raman lines. This is the CB lines here. When we do the oxidation, we see this is the oxide lines I was showing you before, and we clean off everything else from the system, except we have a little bit of gold chloride here, which was a clue. So when we go back, so this is all now done electrochemically. We can do this in plasma. if you want to. You can oxidize in any way. But the simplest way to do it is electrochemically, because then you can just take a 1.5 volt battery and do it in any standard salt solution. So it's completely trivial to do this. So here, this is just in a simple electrochemical cell. As we reduce the system again, what you'll see is that this gold oxide first produces this line here. And that line there is gold chloride. So people hadn't understand the importance of gold chloride in the system specifically. And then only when you replace the gold chloride does this Cb molecule come back. So our best picture of what happens is the gold oxide plugs the gap. But the first thing that changes is the gold oxide changes to a skin of gold chloride. It's actually like a surfactant. Gold chloride is an extremely strange polarizable material. It's not ionic, it's covalent, but you slightly change the chloride-gold distance and there's very strong charge transfer. That turns out to stabilize those facets so that then the Cb molecules are attracted in and rebuild the facet from the Cb outwards, so it makes extremely precise, even sort of better gaps each time that you do this. So there's a lot of sort of interesting gold chloride chemistry in here. So we don't have to, when we're doing the electrochemistry, we don't have to oxidize the system. So now I'm going to show you what happens when, how we can use this to also add a degree of separation into the system. So here I'm looking at all of the DNA bases, which are just floating around in solution. And what we're doing is we're applying a potential cyclically like this, but we're going to too small a potential to oxidize the gold. So we're just making the electrode more positive and then more negative and going backwards and forwards. And what we're doing here is you can see that this is the Cb lines and this is the adenine signal, for instance. So the adenine signal, we start to see it, but over these cycles, it continuously increases. If I just leave it in the solution, it doesn't do that. So this cycling is absolutely crucial because it greatly increases the signal we see and therefore the signal to noise in the system. So we can use this with all the bases. We can distinguish all the different bases in there. You can see there's also very interesting Stark shifts. So the way that ions dress these molecules changes their vibrational energies. And then we can plot the signal size as a function of the potential as I sweep it backwards and forwards. And you can see that different molecules have peak signal of different vibrations at different potentials. This is another way to then distinguish different molecules. So we have to understand how does that work? So we actually teamed up with this Korean group of Hongjin Kim. And so basically, they're the only people in the world who can do molecular dynamics and DFT that involves the water molecules at the metal surface with a field and the ions and the analyte. So it's interesting how theory is not yet capable of really properly addressing the system. But what we managed to show was that what happens at zero potential is that these molecules tend to like to lie flat because of van der Waals bonding between the molecule and the gold. But as you put on a potential, because they've got a permanent dipole, they lower their energy by making the dipole along the field that you've applied, this electrochemical field. So they stand up. And then, in fact, they lift off, which is why the signal goes away. So essentially, by looking at the balance for these, you can see why these look like this. And then we have a whole catalog of different molecules. And in fact, as these rotate, you can see different vibrations line up with the optical field. So each vibration shows a different signature. So it allows you really a good way to separate different molecules. We can also do things like look at the water. So whenever you make a plasmonic structure, my group tell me it's dry. And I go like, it's a nanostructure. It's never dry. There's always some water around in these nanostructures. So here what we can do is see it directly. If I just immerse it in water and I look at the OH stretch around 3,500 wave numbers, I see quite a sort of broad band, which is very typical of what I see for water with hydrogen bonding. But if I actually dry that out, then I lose these lines here. These lines come from hydrogen bonding. So when I have two water molecules interacting with each other, then this one here steals some of the electron density from this bond, so that actually it decreases the energy. But if that hydrogen bonding goes away, which is what happens here, then I don't see it. So in fact, what we feel is that there's actually a monolayer of water sitting in the gaps. You can desorb it by heating it. And actually, by doing electrochemistry, you can see there's actually a whole set of different lines here, which come from essentially these dimers, which are aligned to the surface. So at negative voltage, these are hydrogen down. And I can see the different stretches. I mean, there's asymmetric stretches, and they're coupled together. So we can understand quite a lot about water in these constrained gaps, which is not really very understood yet. We can also use these to detect gases. So for instance, we've made the optical nose where we're able to detect ammonia at part per billion level, which turns out to be extremely difficult using any other sensor technology. And there are a lot of other volatile organic carbons or organics that you can detect in the same way. So this is sort of now combined into a big UK project called MetaHub, which is trying to bring the use of 3D metamaterials, so these are not really metasurfaces, together to really try and look at how you can make new sorts of materials, and this is a good paradigm for it. So I'm just going to show you in the last few minutes where we've been going with this. So I've shown that you can detect these small molecules that fit inside these gaps. So there are less than about 5 kilodaltons. And we've been concentrating to start with on hormones and neurotransmitters. One of the directions we're looking at the moment is IVF, so looking at follicular fluid and embryonic fluids to increase the percentage of implantation successfully, which is a big issue. So this is, in this area, there's perhaps 4,000 small molecules, but people really don't have a way of detecting them all. They're rather unknown, and certainly how they change in time. But there are many other areas where this can have impact. So as I said, it's easy to detect cannabinoids in the system. So we talked to the Home Office, or sort of food security, so methanol contamination in alcohol for all of us going out in the evening, or looking at bacteria or fermentation, so you can see all of these products easily. We've also been looking at how bacteria talk to each other. So bacteria in a biofilm talk to each other by exchanging these small molecules, particular ones. It's not easy to measure them. At the moment, we can measure them now easily. And now we're trying to get to the stage where we measure a single bacteria talking. So we're trying to listen in to a single bacteria talking to its neighbors. And again, that looks viable. I talked a little bit about environmental sensing, and more generally in agri-tech, you want to detect a whole range of things. This introduced me to the robotic dairy in the vet school in Cambridge. So we're looking at now hormones in cows and when they're lactating. And the key thing is to drive down the potential cost of this. So what we've managed to do is to build a demonstrator. It's about this size. It's got a computer, but that's the big bit. And there's no reason it can't be built quite a lot smaller than that. So it just has little cartridges which you can use for a day and then maybe throw them away as well. And the monolayer aggregate sits right in the middle there, and it's very easy to apply these potentials. And just to show the sort of things that we're now doing, so this is looking as a function of time. That's the Raman spectra I was showing you before. And I have quite a complicated potential that I'm applying here, which gives me a particular current. So what I'm doing in each one of these, I'm doing this cycling to increase the signal. And then what I'm doing at the end of that is I'm measuring and then I'm cleaning everything away. And I've got a small amount of separation of the molecules in front of that. So essentially I can look at all the molecules as they come through and fingerprint them. So for instance, this is a whole mixture of different things: cytosine, hypoxanthine, xanthine, adenine, tryptophan, and so on. So you can see them arrive, and so it's fantastic how accurate you can make this work now. And there are lots of different ways to separate it. So the reason that you do this clear out is that if you've got a lot of one particular molecule which has a large signature, if it sticks onto your sensor, then you're masking everything else. So what you have to do is be able to get rid of it, and that's what this allows you to do, which is called the memory effect. And there are lots of different ways that we can actually do multiple separation. We can make different little bits on the same chip that have different functionalization inside the gap, so more or less hydrophobic or sensitive to pH. We can change the gap sizes. We can look at the separation time. So it allows us to make a really sophisticated sensor. And my point would be that only by getting good data like this will machine learning and AI really make an impact. If you've just got grunge, it won't get anywhere. So this I think, is the advantage here. So what I hope I've done is I've convinced you that trapping light in these nanogaps really takes you in some interesting directions. And you can see that this is a wide range of different disciplines. I can't tell you which bit's the physics bit or the chemistry bit or the materials bit. It's just nanoscience, nanotechnology. So I'm really thankful for my group who span all these disciplines and who've pushed this through. And I've shown you a whole range of different things. One of them is that actually the oxidation of gold is super useful. incredibly helpful for making all this work. I've shown you that you can make really intricate metamaterials from these structures, which have refractive index that we should be able to push above 10. We've got to 6 so far, and we're still working on it. And that opens also lots of sensing opportunities. And then it allows you to get into the science. For instance, if there's only 4 layers of water molecules in the gap, how do they structure? And we're seeing all sorts of interesting things on that. So with that, I'll thank you for your attention and happy to chat.
Thank you very much for the fantastic talk. Questions, please.
Thank you, Jeremy. Fascinating talk, outstanding results. So the question for you is the following. It seems that for me, the problem is getting light in and out of your systems when you are increasing the number of layers. And you have a trade-off between how sensitive you are and also when you introduce something in your gaps now, the molecules, what happens to your capacitive change and how vibrations, the vibrational spectroscopy changes?
So many interesting questions. So the first question was about, can I get light through a thick structure? The theory tells us actually, yeah, I mean, it's a low loss structure, but that's for the perfect structure. So we're trying to understand the effect of disorder and actually learning how to control disorder in the system. And I think that is an important thing. For the SERS measurements here, we just need a monolayer. That's fine for us. When we combine them, then you have to play a bit more. But then you also make a really good point. How do the molecules change when they're put into this environment? And in some ways, it's embarrassing. The SERS spectra there are absolutely repeatable, the same every time. So that's great for SERS. But if I do the most advanced DFT in the world, I still don't get that spectrum because the DFT doesn't properly include all the metal around. And the instance of that is still not properly known. And I think it's because it's not just the molecule, there's solvent, there's ions around. It's a very complicated system to really understand. Only now we're starting to get there. So it's a very good question.
I want to follow up. You had just one slide about the detection of bacteria. Now, you know that the leading cause of death in hospitals everywhere is actually sepsis. Mm-hmm. And the reason is that by time they actually find out what it is, if they are capable 2 or 3 days, and many patients die. In Europe, just last year, there were 3.4 million cases of sepsis, 700 people die. It doesn't have the attention that it should get. So my question to you, if you have any thoughts, how to...
Yeah, I mean, it is an important direction as well. We actually have been more focused on UTIs at the moment. So a similar sort of thing, you want to prescribe the right antibiotic immediately. I think this is, what we have done so far is we can tell the difference between pathogenic and non-pathogenic E. coli, which are responsible for UTIs. And it's because they talk to each other differently, interestingly. And I don't think people really understood that or understand much about the signaling. So at the moment, I think it's really interesting. We'll have to see where we go. We're learning how you can't actually just put bacteria and grow them on top of these gold structures, because bacteria don't like it. So you have to design how you're going to make this, how the molecule is going to come there. But I think we will be able to get there. I think there will be a low-cost device that will go into clinic, which will be able to do that. This is true.
Can I?
Good fight. Hi, Jacob.
Jeremy, intuitively, you actually, all the work on Plasmonics has shown that the best you want to randomize to get a localized mode, because it's non-linear process. Second part, once you have a very small gap, in fact, your molecule, if it is there, it modifies the gap, and probably you do get your localized state right where the molecule is, because you have a defect.
Well, that last point is really interesting. We've even talked about if the light is so confined in the gap, then can I think about refractive index of a layer of molecules, or is the local refractive index of the molecule on the nanometer scale actually confining my mode itself? And certainly with the picocaptors, when you have these single metal atoms, it's absolutely clear that you localize the field. I think the jury is still out on the refractive index of a molecule. We're still trying to understand what that really means. But we have some evidence, well, we have very strong evidence now that normally when you think about a spacer in a gap like that, then it has a refractive index. It's a polymer, right? It doesn't matter how thick or thin it is, it has a refractive index. This is not true when I stack molecules, because I have to think about my molecules also as a metamaterial. So it depends on their organizational arrangement what their refractive index is. So we can see in some cases when we stack molecules that the refractive index changes extremely strongly. So I would agree with you. There's a lot of interest there.
Jeremy, fantastic talk as usual. Idea came to me during your talk. I think it's about 15 years ago, there was a group in KAIST led by Professor Shin, who demonstrated exactly the same structure, a layered gold structure with small gaps, which was a very, very highly refractive index in the terahertz part of the spectrum. My question is whether there's any perspective for sensing going down the frequency and still observing, say, I don't know, Raman shift or something like that without light, just based on microwave.
So terahertz, I think the answer is yes, and we're actually doing experiments at the moment on trying to do that. And I also thought, it goes all the way to DC. But the thing that we forget is that there's a penetration of the light also into the metal. So I think the answer is, this is what we're trying to do at the moment. If I can use nanoparticles up to about 400 nanometers in size. So that's what gets me into the terahertz regime. But if I just look at the penetration, it's not the same as the skin depth. There's a different scaling to that. But I have to be careful of that. So I have to just decide that. But I think in the end, one should be able to do that.
But are there interesting, highly selective resonances which will allow distinction between different molecules in terahertz?
I see. Certainly I think the answer is yes, because there are all these vibrational degree of freedoms. Yeah.
Thank you very much. Okay, last question.
Very quick comment and question. Raman sensitivity goes inversely with the wavelength, so it might not be that great of an idea. But I had a question. Is there an effect of chemical potential of the metal and the molecule that modifies the molecule Raman response?
So this is what people would know as the chemical shift, which has been like endless, 30 years of discussion backwards and forwards how important it is. Yeah, exactly, chemical enhancement. So, I think, so you can think about it as charge transfer to the molecule. So I think the answer is definitely that has some effect. The way that I've seen it happen, you can look at the works that we've done on these picocavity generation. So if I think about the field that's being generated at the metal, then if the molecule, the tip atom on that molecule is very polarizable, then what happens is I also induce a dipole there. That dipole is enormously amplified by its proximity to the metal. So I end up with very, very strong dipole-dipole interactions with any polarizable tip atom close to the metal. And I think that is the part that is the strongest effect. And that yet at the moment cannot be included in any description because my plasmon's classical and my DFT is quantum and they can't be put together yet. So I like to say it's a failure of theory and I encourage theorists to not fail.
Well, thank you very much, Professor Baumberg. We have to move on.